Okay, boys and girls, we're on page 80 in our science book, and we're on exploration number 3. Okay. And this is called Which Way? Which way?
Exploration 3.
Which way, toward or away? The direction that a force is applied matters as much as how strong the force is. When you push something, you use force to move it away from you. When you pull something, you use force to move it toward you. More than one push or pull often happens to an object at the same time. Also, different forces may be applied in different directions.
Okay, so we're going to watch the video to discover more about forces. So we have the 2 dogs there. And so we're going to watch that video and see what happens with the 2 dogs and what happens. It says the dogs are playing a game like tug of war. The strongest pull wins. So let's look at our video. What's going on with our video?
I think it's a turtle. It's a lamb. Yeah, that's a lamb. That's a lamb. I just put some flower cakes on the trees. There we go. Oh my gosh, look at that. Ooh, look at this one. Look at this, Irene. Look at that. Look at that thing. Dude, that thing is horrible. At 276.
Okay, now maybe we're going to work. Apparently, you're never supposed to watch the video because then it doesn't want to rewind itself.
These dogs are playing a game similar to tug of war with a round plastic disc. In tug of war, 2 forces are pulling on the same object but in opposite directions. If the forces are balanced, the object will stay in one place. If the forces are not in balance, the object will move in the direction of the stronger force.
Okay?
So,
Let me ask you this. So, what would happen if one of the dogs suddenly stopped pulling the toy? What would happen if one of the dogs stopped pulling? What do you think would happen? Olive.
the other dogs would get it because they stopped pulling it away from the other dog.
Okay, one of the dogs would get it. What else would happen?
They would let one of the dogs play.
Okay, so one of the dogs would stop pulling, and then what would happen?
It would have like pushed away.
It'd get pushed away. Libby?
The other dog would fall down.
The other dog would probably fall down. He'd probably stumble for sure. Okay, so the dogs, so do you think the strongest pull is definitely going to win, right?
Yeah.
We've seen tug of war before. When have we seen tug of war? When have you seen tug of war? When have you seen this actually in action? Maybe not with dogs. When have you seen it, Elisa?
I've seen it in a challenge.
In a challenge, Mikey?
Before all this, and even a few years ago, our school actually did it.
Our school has it, right?
Yeah.
We have it on field day. We have tug of war on field day. That's right. And what happens when one team starts to lose their grip on it? What happens to the players on the other team? The other team, they all go what? Juliana?
Fall.
They all start to fall down, right? They all start to fall down. Very good. So here, so we saw the dogs are playing with that looks like kind of like a frisbee. So let's look at these statements, and so we were watching them. And so which statements about the video are correct? So we're gonna select all that apply. So let's decide if these are correct. Both dogs are applying force by pulling on the toy. Is that correct? Are they both applying force?
Yes.
What do we think? You can give me a thumbs up or a thumbs down. Okay, I'm getting thumbs up, so I'll check that. Only the stronger dog is applying force by pulling on the toy. What do we think? Okay, I got a thumbs down, so I'm not gonna do that one. The motion happens in the direction of the stronger force. So is the motion happening in the direction of the stronger force? What do you think? Okay, so I got thumbs up on that. And then it says the dog pulling with the stronger force might also pull the other dog toward it. Do we think that's happening? So I'm getting a thumbs up towards that. So let's check and see if you're right. Well done, it says. Well done. It says both dogs are applying a force. The stronger force will cause the motion to happen in that direction, and the stronger force could pull the other dog toward it. So the stronger dog is applying more force, and it's going to pull the other dog toward it. Very, very good. So that's what's happening in our video. So let me ask you this, boys and girls. What experiments should a toy designer conduct to make a toy that could survive frequent tugs of war between two dogs? What do you think a toy maker, a dog toy maker could do? Yes,
Like a long rubber snake.
a long rubber snake. What else could they do? What do you think, Logan?
So it's like harder so it won't rip.
Something, so the fabric's like harder so it won't rip? I think that might be a good idea. Jensen, what do you think?
I would take a long rope for both dogs to tug, and then I would add like rubber around the parts, and then I would leave the tassel for them to tug on.
Oh, so you would put some tassels on the ends of it, and you'd have rubber around it, making it harder for the dogs to rip it apart? Very good. What would you do, Kelsey?
I'd make it out of rubber.
You'd make it out of rubber? What would you do, Avery?
I would make like a very like I just use a regular rope. Let's make a very long rope so
You-
that they each have their own side to pull on.
Okay, so you'd make it out of regular rope, but make it very long. What would you do, Ivy?
I would do like a rubber rope, as like Avery said, but like kind of I would do like a kind of like rubber tire,
Okay.
and then they can have their own sides. When it's a circle, they have their own sides.
Oh, so there'd be like a circle on the end, like a circle for them to grip onto? What would you do, Mikey?
So the tripod tires are rubber. I would expand the quality about 10 times and make it a dog toy, so that it's basically it's gonna last a very long time, maybe a few years.
Okay, very good. Because I know that my dog, has got very strong jaws and sharp teeth, and she can really rip a toy apart. And they make these toys, they're made out of fire hose material, and she can still tear them apart. We can't seem to find toys that she cannot destroy.
They were like
She destroys them like crazy.
Oh, please
They don't last very long.
break their teeth. They were like
Yeah, oh, I'm sorry. Oh, no, well, that wouldn't be fun for her to play with a piece of metal, Teddy. Yes, Olive.
a metal. Break the
Excuse me.
So when we get my dog's toys, she'll literally rip the toy and take the squeaker.
Oh, yes, the squeakers. I love the squeakers.
Yeah.
Okay,
Yeah.
so now let's take it further. It says discover more. Choose one of the paths below to continue your exploration. Do we want to do simple machines, predicting motion with golf, or careers in science and engineering? So let's take a vote. Who'd like to do simple machines? Raise your hand. Because we've kind of already studied simple machines, right, boys and girls? We did some things with simple machines. Who'd like to do predicting motion with golf? Raise your hand. One person. Who'd like to know about careers in science and engineering?
Oh, I meant the careers.
Okay.
Oh, here's the page. Where's that page?
So let's see, it says, careers in science and engineering. A safety engineer makes products safer for people. Watch the video to discover more about safety engineers. Is that going to get bigger? Oh, maybe I need to come do it at my computer.
They're like dogs. They're like wild dogs.
You are in the bike helmet impact lab, and here we test helmets. This particular test raises up the helmet so that it reaches an impact velocity of approximately 11 to 14 miles an hour, and that is roughly comparable to a lot of bicycle helmet impacts and injuries. This is an important test because it ensures that bike helmets comply with the federal regulations. And in this particular example, like I've got in my hand, on the outside, looks very, very similar to anything else that you would see in the marketplace, and yet it broke. So that's why we test.
Oh, so there you go.
He made sure it worked.
Yes, he made sure it works.
Break it down.
Take it further. Discover more. Choose one of the paths below to continue your exploration.
Simple machines, predicting motion. Golf.
Careers in science and engineering. Careers in science and engineering.
Safety engineer. A safety engineer makes products safer for people.
So safety engineers test items that people use at home. For example, a safety engineer might use a machine to drop a bowling ball over and over into a chair. That puts force onto the chair seat as if a person sat in it many times. Safety engineers understand that forces have strength and direction. They use that knowledge to make things that are safer and last longer. So that's one of the things a safety engineer will do. So they'll be testing things to see if they are safe for people. So then you looked at that bike helmet and you wondered, gee, how safe is that bike helmet? Did that bike helmet seem very safe to you? And that's the type that they sell in stores, boys and girls. So a safety engineer will check the safety of the different things that are being sold to determine exactly how safe they are. That was pretty interesting.
This one's very heavy, but it's still breaking because wind on our head. So this is better. I don't even use a helmet, so. What? I ride around my bike with a helmet. I didn't have to build it. You wouldn't want so.
Take it further. Discover more. Choose one of the paths
So
below
let's
to
do this
continue
one.
your exploration.
Simple machines, predicting motion. Golf.
Careers in science.
Predicting motion. Let's predict the motion with the golf. Golf and miniature golf look about the same, but how do their forces compare? In both sports, the club pushes against the ball, making the ball move away. How much force is needed to make a hole-in-one in miniature golf? And then here we have the golf tee is hundreds of meters from the hole. How much force is needed to get the ball there? So how much force, if we're comparing those two, how much force do you think you need to get the ball in the hole-in-one in miniature golf, and how much force do you think you need to get the ball from here to the hole? Do you think it's a comparable amount of force, or do you think the force is different for both of those? Ivy?
Well, for like golf that you need to put in the real with the air, you need a lot of force because the pole is normally really far away.
So the hole's really, so in this one, in regular golf,
But in miniature golf, you just need a little push because they're normally not that far away.
they're not that far away. What do you think, Logan?
So, for the non-miniature, the real one,
Okay.
you're gonna need to hit it way harder. Just because usually you have to, sometimes you have to hit over a lake, and it could be a bad day if your ball lands in a lake.
Right?
And then, just so it can go in the hole. And then miniature golf, you need to do like a medium swing, just because usually there's obstacles.
Okay.
If it's an obstacle, it could bounce back
Mhm.
and go into the hole still.
Yeah, because sometimes there's obstacles in the way. Teddy?
You have to have the right amount of speed in miniature golf because if you hit an obstacle too hard, it could bounce right back at you.
Yes, it does.
It could go too far behind you and you have to restart, but a lot further back.
Yeah, it does that.
And then in real golf, you have to hit it a lot harder because if you're gonna get it in the hole, you can't just go. Because the hole would be maybe sometimes a mile away, and you have to hit a lot harder than just miniature golf to get it in a mile away hole.
Well, I don't think it's quite a mile away, but it is kind of far. So, you have learned that a stronger force can produce a greater speed. This is especially important in golf because the ball has to travel faster and farther. The club hitting the ball has direction as well as strength. This is very important in miniature golf. In miniature golf, there are many things in the way that you have to move the ball around. The ball must move short distances, but it must move in just the right direction. So you're right, you're talking about obstacles. So not only do you have to move your ball, you have to move it, number one, in short distances, but you do have to move your ball around different obstacles. Because see, look how he has to move it around these obstacles of these logs here. And so sometimes you're hitting the ball and you want to use, maybe you want to hit maybe the sides to bank it off those shots to move it around things, right? And then here, you have that open course, and you have to do what? You have to hit it long and hard. So let's see if we can figure out the correct word here. It says, the golf club hits the ball with much stronger pull direction or force in golf than in miniature golf. So the ball moves faster and farther. So what word are we going to do there? What word is going to fill in the blank there? Clark, you golf, you tell us. What do you think? The golf ball hits the golf club hits the ball with much stronger blank in golf than in miniature golf, so the ball moves faster and farther. What do you think? What do we have to hit the ball with? Pull, direction, or force? You think it's direction? No, that's not it. So what can we try? We're going to try again. Who else can help us try to figure out what it is? Ethan, what do you think it is?
Force.
Let's see if it's force. It's force. Force is the push that makes the golf ball move. So you're hitting it with force to get it down the fairway. Okay? So in which kind of golf game would you hit the ball with a weaker force? In what kind of game would we hit it with weaker force? Juliana?
Miniature golf.
Miniature golf, we would need weaker force. Maybe if you're putting, you might need weaker force. Those would be examples of times you would need weaker force. Okay, I want to find back where it says direction matters. Where does it say direction matters? On 81, where is that? How did I get away from that?
I don't even know where you are. You have to go back maybe because a lot, because we don't even know where you are. Yeah. I don't even think that's okay.
All the way at the end of the hall.
Okay. You're welcome. Oh, we have Spanish? Yeah. We have Spanish tomorrow? We have it next Monday. Next
You have it tomorrow.
Hooray!
So direction matters. You know that the direction that a force is applied is important. In air hockey, pushing the puck in the wrong direction can make you lose the game. Who here has ever played air hockey? Air hockey is so much fun.
That's so much fun.
It moves. Okay, boys and girls, you can't keep talking. The game moves really fast, doesn't it? The puck is moving all over the place. And you're trying to move the puck into the other person's goal. But you're trying to use strategy about where you're hitting the puck, right? So let's look. It says players use mallets to apply forces to the puck. The force of the mallet changes the direction of the puck and sends it into the other goal. So these are the mallets that they use. So let's watch this.
I love Oh, that was nice. Oh no, these are strategy. Game over for us. How do you know the roller? Ooh, ooh, that was great. Oh, that was good. That was pretty good. And here.
Okay, so what were the different ways? So when we're looking at it, let me minimize this again so we can see what we're doing. So let's look at that. So they were using the mallets to move the puck in different directions. The first way, what did they do? Do you remember what they did the first time? What they do? They just used the mallet, and what they do with the puck? Juliana?
They just hit it in the goal and he started moving the puck sideways.
Yeah, they just hit it right in. It just went straight across, right? What did they do the second time? Do you remember what they did the second time, Avery?
They got it in the goal.
And how they do it? One of the times they hit it into the sidewall, right? And they used the force. That force banked it off the sidewall into the goal. So that was another way that they were able to use force to score a goal. Now, so I want you to look in your book, because you have two pictures in your book, correct? Okay, so it says in your book, it says players use mallets to apply forces to the puck. You have one where it's going straight across, and then you have two. It says the force of the mallet changes the direction of the puck and sends it into the other goal. Let's look at the question. Do you see 14? It says, what force sets the puck in motion? So what force sets the puck in motion, boys and girls? I don't think this is a question, right? Is it a question here? Is it a push or a pull sets the puck in motion? Teddy, what sets the puck in motion?
A push.
A push. By the mallet set the puck in motion. It also changes the puck's what? Weight or direction. What does it change? What does it change? Yanni? It changes the weight or the direction?
Direction.
Very good. So the mallet is used to push the puck. When the mallet pushes the puck moves in a different direction. Okay? So here's what we're going to write. Because you have got room to write there on your paper. So this is what we're going to write, boys and girls. We are going to write a push from the mallet. This is question 14. A push from the mallet both sets the puck and changes the puck's direction. Oh, I don't need an apostrophe there. And changes the puck's direction. Okay? So you guys can write that down. Okay, turn your page. We're not gonna answer what's on the next page. More force or less. Now pretend that you have to choose between two paths for your dog sled. You could signal, remember the dog sled?
Yeah.
Now pretend that you have to choose between two paths for your dog sled. You could signal the dogs to pull the sled along a level path. The other choice is to take a path that goes up a steep hill. How will the dogs use force differently along these two paths? Okay, so I want you to think about that. Choose the correct words to complete the following statements. Okay? You choose to try to drive the dogs up the steep hill. That is the decision you have made. You've decided you're gonna go up that steep hill. They move slowly. Then you take them to the level path. They run quickly. It takes more or less force to pull the sled uphill. So what do you think? How much force does it take to go up the hill? More force or less force to go up a hill? And you could think about how it is when you are moving uphill. Does it take more force or less force to go up the hill, boys and girls? What do you think? Elisa? More. Let's write more here and see. It takes blank force to pull it over level ground. How much force do you think it takes just to pull the sled over level ground? What do you think? Logan? Less. Let's see if you're right. Very good. It requires more force to move the sled up a steep hill than it does to move it across level ground. It's harder to go up steep. So boys and girls, I want you to fill that in your book. Fill in those words. Fill that in. Because the force required to do that is more. Did everybody write that?
Yes.
Okay, and now we're gonna write a sentence here. And this is the sentence I think we should write here. This wants me to type, I'm not gonna type, I'm gonna write. In your book, we are going to write a sentence, and our sentence is going to be about forces and walking up and down, walking uphill or walking on level ground. It says, number 17 says, write a sentence about going uphill or walking on level ground. Use the term stronger force and weaker force. It takes, this is number 17, it takes stronger force to walk Is it gonna take a stronger force to walk uphill or on level ground? Somebody tell me. Juliana,
Uphill.
to walk uphill. And we're gonna say a weaker force to walk on level ground. I think we're calling it, yes, to walk on level ground. So let's write that. Yes. Yeah, no, you can't. I'm sorry, we're busy. Okay, boys and girls? Now, here's what we're going to do. I want us to go to page 85. Go to page 85. Oops, I went the wrong way. So boys and girls, what we're going to be doing is next time, we are going to be, next time we meet in science, we are going to be doing pages 85 through, I think it is 87. That's what we're going to be working on, 85 through 87. 85 through 87. We're going to be doing that. 85 through 87. Okay? So that is what we will be doing next time in science, 85 through 87. So boys and girls, I'm going to have you get ready to put your science away.